Hi Spring fans, welcome to another installment of Spring Tips. In this installment, we're going to take a look at the wonderful and wide world of network programming and reactive programming and relate them to blocking and non-blocking I/O in particular. Remember the goals when we write reactive code. We want scalability, we want ease of composition, and we want robustness. Reactive programming supports that first goal, scalability, because it makes it easier to write code that handles a large number of requests. Let's take a look at a pathological example first. Suppose you run a restaurant and you have a few open tables, and let's also suppose, for reasons completely unrelated to this example, the restaurant is called Food Factory Bean Cafe and it's on Spring Street in Springfield, USA, because that's exactly what I would do if I had a restaurant. Now, you're the only waiter on staff at the moment, and a party comes in and you, the waiter, sit down with them and wait for the entire duration of their time in the restaurant, promptly handling any requests but ignoring any other parties that happen to come in. In this scenario, the party you served is happy, exceedingly happy. They got your full attention and prompt, courteous service. The service for them was quick, but for everybody else it was unavailable. And so naturally, people aren't happy. This approach doesn't scale. I mean, just think about it, right? Like the restaurateur would have to hire more staff every time they added tables. You can make this arrangement work, but it's expensive, right? You can add more instances of the server, for example. You can create more restaurants or add more waiters or whatever, but it's expensive, right? In this example, this is more or less blocking I/O with something like the Java I/O packages. We can look at a simple example to kind of see it in action, but it's pretty simple. Let's start with a baseline traditional blocking I/O example. When I say blocking, the client, from the perspective of the client, things come to a standstill until something else finishes. This has the benefit of being very easy to reason about, but it's also limiting in our scalability. Synchronous and blocking I/O, however, couldn't be more accessible. Let's give it credit where credit's due. It's very easy to understand. The example was felt and approachable, but again, bad result. So I do think it serves as a bit of like pseudocode. We have server sockets, which take sockets, and then there's I/O, right? Let's write an example that uses traditional blocking I/O. And so this will just be very simple. We'll start this project, and I'll just keep adding to it in my IDE, okay? So we're just going to call this I/O. Sure, why not, right? We don't care. And I guess I want Lombok. I want Java 17. And perhaps the reactive web support, although I'm not going to build a web application. I just want to have the libraries that will import for us. So we'll hit generate, and we'll open this up in the IDE. Okay, so our example is not going to be a web application. We're going to build network services, but obviously we don't want it to actually create a web server, so we'll say that the application type is none, okay? And then in the I/O application, we're going to create a few simple implementations of a given interface, right? So that interface will be interface, let me see, network file sync. And basically, we're just going to consume. We're gonna start a service that consumes data, and we'll write it in such a way that it'll give us back the bytes that have been sent to it from a network call. Yeah. So there's this. Maybe we can even just there you go. No, actually, you know what? Like that, it's better. Okay, so there's our basic contract, and I want to implement this. I want to create an implementation using synchronous blocking I/O. So this is the easiest one to get right. We don't have to do a lot of work to make this work. And you've probably written something like this in university. Okay, so class I/O network file sync implements network file sync. Okay, and we're going to, it's just a Spring Bean. We're going to go ahead and I'll just call it a service, why not? In order for this to work, we're going to need to use the Java I/O types. We're going to have a server socket. Okay, so try var ss equals new server socket. And we want this socket on the port that we've been given, and this server socket is auto-closable, right? But it could throw an exception, so we'll say at sneaky throws, voila. Okay, there's that. This is a Lombok annotation it'll capture it'll try catch our code basically. Okay, so we want to start, and we have a server socket, and now we just want to busy loop, waiting for new requests to arrive. So we'll say while true, then we want to say try var socket equals ss.accept, and there we go. Socket. Okay, good. So there's the socket. As that comes in, we're going to get an input stream and an output stream. So this will block, right? This operation is a blocking operation. It won't proceed. Nothing will happen until a socket connection is made. Yeah. So once that's true, then we can say that in is equal to the socket dot get input stream, and out is equal to the socket get output stream. So now we have our basic network loop, our busy loop. What we want to do is we want to read the data coming in from the request via the client, right? So let's get the bytes. We'll call this byte new byte 1024, and we're going to read some bytes. And the basic pattern here is, you read until you get -1. That means that there's no more to read. So we'll say while read is equal to in.read bytes, and while that does not equal -1, write out the data. Okay, so write, and the data that we're going to write out is the data that's been read from the stream and put into the byte array. Now, you might think of it like a stream, and each byte array is like a scoop. Okay, we're going to take data from the stream of bytes in our scoop, and then we're going to pour it into another bucket. But we don't want to, we might have some sediment left over from the last time we scooped. So what we want is to only get the stuff that we've scooped out this time around. The other stuff might be from the last time we scooped. And the metaphor is, it doesn't quite exactly work, but the idea is that we don't want to copy from this array stuff that was from the last scoop. We only want to copy what we got on this time through the loop in this scoop. So we'll use out.write 0 and then read, right, the number of bytes. We're going to start off at the 0th element of the bytes array and then continue until the number of read items. Read will never be larger than the array element, length itself, so it'll never be more than 1024 elements. Okay, it'll be at most enough to fill the array. Okay, so while we've got that, so we've got our abstraction. Let's create a simple example that uses the Java IO abstractions. So class IO network file sync implements network file sync. Okay, here's that component, and this is going to, it's a very predictable skeleton, right? We're gonna try to listen for new requests on a server socket, right? So server socket port, okay, and it'll be sneaky throws. Good. And for each, once we have a socket, once we're out there waiting for requests, we'll say that we want a busy wait, we want a busy loop. So we'll say try var socket equals ss.accept, and that'll give us a pointer to a socket. The thing is, that call there will block. It'll block until we actually get the socket that we want, right? So until a client makes a request, we will get nothing. It'll just sit there on that thread waiting for that to happen. As soon as that happens, the execution on the thread of execution will continue unblocked. So the next thing we want to do is get the input stream representing the data coming from the client. Okay, and we also want to have an output stream in which to collect all the bytes. So I'm going to create a little byte array output stream, and I'm going to create a little, like a scoop, if you will. Right? I'm going to scoop bytes out of the stream of data. So 1024, that'll be this. Okay, and we'll say while in.read bytes, or let's say bytes. Let's call that bytes. While in.read bytes is not -1, but we also need to capture. What this means is, it says I want to read as many bytes as we can until we get no bytes back, -1 bytes back. But I need to capture how many were read. So I'll say var read equals -1, and I'll say read equals does not equal to that. Okay, and with that value, that number, we can then write out the data. So we'll say out.write this array starting from 0 up until red, and red is some number less than 1024 in this case, because our array length is 1024, and some number greater than 0, presumably. And we're going to keep going until we reach the end of the stream, which is denoted by -1, and then we're just going to accept everything and write it out to the consumer. Okay, so it's called the bytes handler. I'm going to accept the byte array, right? So we'll say out.toByte array. Good. So that's the basic implementation. Yeah, that's just it's a pretty trivial implementation. I think it's pretty easy to understand. What are we doing? We're creating a loop, we're creating a service socket, we're looping, waiting for incoming requests, getting an input stream, getting an output stream. And obviously the problem with this is that if for whatever reason the incoming request has like 5 hours worth of data to send us, then this loop will never proceed to the next iteration until those 5 hours of data are all read in. You see what I'm saying? So if there are any other requests that arrive, they'll just be ignored. We will never get a chance to process those. They'll just be sent back. So one obvious optimization here is to spin this out on a thread, to use an executor service or a thread pool to launch the requests so that they can be processed. So for each new request that comes in, kick off a new thread. Obviously, this has an upper bound. You can't create an infinite number of threads. All right, so we have our implementation, but obviously nothing is running this implementation. This is just an interface that we created. There's no contract anywhere here that indicates that Spring will know what to do with it. So I'm going to create a simple bean to run it. Okay, so we're going to say application runner, process it. I'll inject the implementation, sync.start, and port equals, let's say 808. So, we'll say we want to run on port, and the bytes will be here, and we'll just say there are bytes dot length bytes. Okay, there we go. There's our basic loop. So our basic business logic. We're just injecting the implementation, and we're using it. And so right now we've only got one, so that it could resolve only to this particular one. And actually, this could be a service, I suppose. Okay, so that's the first thing that we want to do. Let's see if that works. Okay, so it's running. Now I want to exercise it by sending some data. So we'll say nc localhost 8008, and we're just going to read in the data from this file that I have on my desktop called content. Now, before we do that, let's take a quick look at the file, and in particular, you can see that there's 15,713 bytes. Okay, so let's run this, and there we go. There's 15,713 bytes. So we have something that is successfully able to capture all the bytes, write them out to a file, and then hand them back to our consumer. This is using traditional blocking IO. And again, what we mean by blocking is that whenever we do anything here, we can't move to the next line until it completes. And in this case, we're executing on the main thread of execution. What that means is that we can only handle one incoming request at a time. I could create threads, and that way I can handle as many requests as I have threads. But even there, within that thread, I can't move forward until these operations, things like in.read and so on, complete. They're going to block the thread of execution. Okay, let's try again. Let's suppose a party comes in and you seat them and take their order. And then another party's and you seat them. There's no contention here, but there could be. Now, you're able to handle one and then handle the other, and so you're able to satisfy both tables at the same time. But what if both come in at the same time? Well, here, it's still not necessarily a problem because you can give one table their menus, then disappear, then come back and take their order, and then meanwhile the other table's ready, give them their menus, and so on. And you can keep doing this all night long until the restaurant closes at the end of the night, and everybody should be happy. You're one waiter, but you're able to ping pong between the two different parties and handle them as needed. You spend time actively handling requests, and this is sort of like being on the CPU. You're actively handling things. You're not just sitting there waiting, having a smoke break in the back office. This is kind of like the event loop pattern, right? You're constantly keeping the CPU busy by ping-ponging across different requests. There's a reason why a good waiter can handle maybe 10 tables at a given restaurant, right? And if you want to handle 20, then you just hire another waiter. This is kind of like the event loop pattern. It's a great response to the C10K problem as well, which Wikipedia sums up as a problem of concurrent connections. It's the idea that connections and speed are related is not entirely true, right? The question here is, can we handle 10,000 concurrent connections, not requests per second, right? So you can have a slow service that still handles 10,000 concurrent requests thanks to efficient scheduling. You could have many threads, and each of them operates an event loop. And ideally, you'll keep your service saturated. You don't want to log into your server and find that you've got this very expensive, beefy machine, but most of the CPU is idle because it's just waiting for I/O to happen, right? The event loop pattern implements the reactor pattern, the pattern from which, of course, Project Reactor, which we'll draw a lot on in all things reactive, draws its name. The benefit of this approach is that you can handle more requests, not that any particular requests are going to be faster. If our hypothetical waiter were sat at the table listening attentively for instruction, there'd be no delay at all. However, nobody else would get service. So we don't mind a little delay. That's context switching in the name of availability. Okay. We obviously want our infrastructure to be well used and to be able to withstand the deluge of traffic as well. It's a good problem to have, to imagine that someday we'll have more traffic. So let's look at Java NIO. Java NIO is a different branch of Java that was introduced in Java 1.4 and that supports asynchronous and non-blocking IO. And there's a difference here. For now, we're going to focus on just non-blocking IO. What we mean by that is that you are never going to wait for bytes to be available. All right, now let's turn to NIO. Okay, I'm going to put the previous implementation under a profile. I'll just call it IO, so you can still run this example. It's just that you have to say string.profiles.active equals IO. Let's now build an NIO implementation. So we'll create a new service, class NIO, network file sync, and it'll implement network file sync as well. It in turn is going to use non-blocking IO. NIO can support both blocking and non-blocking input and output. We've already looked at blocking input and output. When we ask for something to happen, we don't get the result until it's ready, but we can't move on in the meantime. With non-blocking IO, all the operations that we make will either return immediately with the data that we've asked, or some sort of error code or status code telling us that they couldn't give us the data that we asked for. But you'll never sit there waiting for the data to be produced, to manifest. So we're never ever in a situation where we don't know when this method will return. It'll return as fast as a method can return instantly. Typically 0 of 1, right? You don't want like log time or anything like that. You want key, in and out access, just like a cache. And so with non-blocking IO, you have that assurance that it's going to return in a finite, predictable, bounded time for everything. All right, let's use Java NIO to implement this new version. Java NIO is very similar to Java IO. The names are basically the same. The concepts are the same. You've got a server socket thing that accepts sockets and then does input and output with it. The names are slightly different. You'll see channels mentioned a lot. Unlike Java IO, where you have an input stream for input and output streams for output, you've got channels which are bidirectional. You can write and read, or read and write from both. Okay. So let's say var socket server socket channel equals equals server socket channel.open. All right, and we want this to be a non-blocking server socket. So we'll say it's false for that. We'll do sneaky throws as well to make sure that it doesn't ever if it throws an exception, we don't have to worry about it. We're going to say server socket channel dot bind, and we're going to give it an address, so new inet sock address port. All right, so now we have a network service on a port somewhere, but nothing is happening, right? So we need to register an interest in accepting new sockets, right? So this is another thing that's kind of interesting, is this is another thing that's very interesting compared to Java IO. You need to tell the runtime what operations you would like to do and to register an interest in being able to do that, because it won't let you just start writing if the thing that you're writing to can't handle it yet. So it'll schedule you. It'll say, okay, I'll call you back. I'll tell you when I can accept a write or when I can do a read and not block right? If I can do a write, because my network buffers are empty and I can just send data and it'll go out on the network as soon as I'm done with it, and I can do that instantaneously, then I'll schedule you for writes. If I can give you a byte array full of bytes instantly without blocking, I'll schedule you for reading, right? There's another operation you can do here, of course, which is accepting incoming requests. This is one of those things where usually it's just the server socket that does this, right? The server socket accepts new requests from which you get just a regular socket. So we need to create a thing that's going to monitor all these different channels for us, and we can then ask for availability. So we're going to create a selector, and if you've ever used the select function in POSIX, then this is pretty familiar. If you've ever used something like epoll or libaio, the idea is the same. It's a way, given a number of file descriptors, to get a status code that tells you that something can be read or written or whatever. Okay, so we're going to say var selector equals selector dot open, and we're going to register the selector and selection key dot op accept. Okay, so I'm saying I would like for this selector to tell me for all the channels under its watch when one of them is ready to accept or to do a socket exception. Okay, and of course it's a server socket channel, so it's probably the only thing that we want to accept requests. The rest of them we're just going to use to read and write from. Okay, now we'll just busy loop as well. We can do while true. Another thing we could have done, and this is a pretty common thread, is to say while not is interrupted, right? But the result is the same. It's effectively while true, right? While true, if you hit Control C, it's the same. Both things will result in the JVM not working. Okay. So let's say selector.select. Notice that I just did a blocking operation. This actually returns values, but we don't care about the values, right? It tells me how many keys are available that I can then work with. But this will block, right? This is a blocking operation. This will block. This is a blocking operation. You could do selector.select now, right? Or now, and this will tell you all the things that are available right now for processing. And so you could use that if you wanted. But I'm okay in this case with just blocking. So selector.select. Okay, good. And once that's finished, then, because remember, by the way, if it's blocking, there's nothing to do. There's nothing on the server, so there's no reason having the while loop do anything. I can just sit there and wait. There's no reason to busy loop. It's inefficient, right? So, but if there is something, then I want to start doing non-blocking IO, because I want to make sure I'm not wasting resources while they're being engaged in satisfying the requests that are coming in. Okay, so then I want to get all the keys. Now, keys are basically little types that tell us when something is possible, what operation is possible, and on what channel it's possible. Okay, so we can use that. We can constantly iterate over all these different channels. We can use those keys to figure out what is possible and on which channel is possible. So we'll say selector dot selected keys, and now we're going to iterate over each key. So var it equals selection keys dot iterator, and it dot has next. Okay, and var key equals it dot next, and then we're going to remove it from the collection. We don't want to see it again, right? It shouldn't get reprocessed. We want to make sure it only gets delivered to us one time. Okay, so we have the key. We're going to remove it from we don't want it to be redelivered, so we're going to remove it. And then now we're going to go through the different states and kind of see in what state they are, right? So if key dot is acceptable, then this must be our server socket, right? And indeed, this will be the very first branch of our loop that will be true, right? So if it's true, then we want to get a socket. We'll say server socket.channel.accept, and that'll return instantly. And then I want to get data about this request, okay? I want to store data about this request. So when a socket comes in, remember, I'm going to get callbacks. I'm going to go through this loop many, many times, and only when a channel is ready to be used for reading and writing, only then will I actually do something. But that means that I might be like several seconds down the line. I might be a minute later, right? I don't know when that'll happen, And because of that, I can't afford to just keep state in this method, because I might be in another thread, I might be somewhere else, you just don't know. So what we want is some way to get a reminder of what we were trying to do with a particular socket. We want some state, we want context associated with a given socket. And so there's this concept in Java NIO of an attachment. An attachment is just it's an object that it's an arbitrary object, any object. You can put a map, you can put your own custom class, you can put whatever, but it gets passed around. So whenever you are doing an operation, you can ask for the attachment for that operation. You can use that to say, oh, okay, now I'm processing this request for Josh versus Dr. Sire versus Madura or whatever, right? Okay, so I'm going to read the data, and then I'm going to create an attachment. Okay, so I'll say attachment, and here I need something, don't I? I need a type that I can use to pass around. Well, this is, of course, the perfect use case for Java records, aren't they? So we're going to create a type here called read attachment, and we'll store some. What do we want to do? We want to store some data in a byte array output stream. So we're going to create a record, which I think is a perfect use for this. So we're going to call this read attachment. Basically, we're going to keep an array of the byte buffers that we read. So copy on write array list, byte buffer, buffers. Okay. So it's just an attachment, just to stash things across the different reads until we're done, and then we'll accumulate all the resulting byte buffers we'll concatenate them all basically into one big array, and then deliver that in toto to the consumer. Okay, so we have this attachment. So we'll say new read attachment, new copy on write array list. Good. And we want to configure this socket to be non-blocking as well, right? And then we'll say socket.register on the same selector, so it's shared now, but this time I'm looking to read data, and I'm passing along this attachment so that it gets handed back to me. You know, it's already been initialized, but I can keep adding to that array list next time. Now, of course, for my attachment, I could just pass along the array list. I don't need to necessarily have the record, but it's nice to have that record. You can stash things associated with the context of this particular request, maybe the user ID or some payload or whatever. Okay, so there's my first branch. So it's going to read, it's now been registered. I'm registering interest in reading. So the next time I come to this loop, I can say if key is readable, right? And that might be the case. It might be that this is readable now. So I'll say that I want to get the attachment again, and it's the read attachment from the key attachment. Okay, there's my attachment, and I want to get 1,000 bytes, or maybe just 1024 bytes, right? I'm going to create a byte buffer. This is a kind of like a byte array, but it's a Java NIO type, and it'll have 1024 bytes length. The channel is a socket channel. Okay, and it'll be key.channel. It'll be key.channel. Now I'm going to read the data, and again it's -1 just like last time. And I'll say if read channel.read bb greater than or equal to 0, then I'll get the attachment, get the buffers, and I'll add the byte buffer. So I'll say add bb. Okay, so I'm basically saying if the read operation returns more than 0 bytes, then take the byte buffer in which those bytes live and append them to the collection of byte buffers that I've got there. Okay, and finally, once I've done that, I want to register interest in reading again, right? So who knows if I have more to do. So I'll say channel.register selector selection key.ops read, and I'll pass in the very same attachment. So we might come back this way through the loop yet again. All right. Okay, so down here, however, if read should equal -1, well, here I'm done, right? We've got all the data. So if that's the case, then I'm going to send the data to our bytes handler, right? So I'll say byte handler dot accept. Okay, and I want to accept it, but in order to accept it, I need to arrive at all the bytes. I need to get all the bytes in one place. So I'll say try var baos new byte array output stream. Remember, a byte array output stream is an in-memory output stream, and it's a great way to accumulate bytes. So I'll say, okay, create the new byte array output stream, and I'll say for var bb buffers, right? So buffers is the attachment dot buffers, and each byte buffer. Okay, so for each one of those, I want to read the data. I'll say each byte buffer dot flip. Right now, those byte buffers are primed, so you can write to them. If you want to read them, you have to flip the position, so it goes back to the beginning, and lets you read from them as though you're reading from the first time. I want to get the bytes, new byte bb dot or each byte buffer dot limit, and then what? I want to read the data from the byte buffer. So I say get the bytes and transplant them, basically transfer them from the byte buffer into the byte array, and then the byte array, well, we can write that out. We can say baos.write. Okay, so bytes, good. Okay, it seems a little twisted, but such is life on the NIO world. Okay, so we have now accumulated all the bytes into the byte array output stream. Okay, so now we've got all the writes to the byte array output stream finished. Now I want to collect all the bytes, so response equals baos.toByte array, and I want to send that to our bytes handler, like so, accept response. And then finally, what I want to do is I want to dispose of the channel. I'm done with it. I've already satisfied the request, so I'll say to please close. Okay, so let's go ahead and run this. Now keep in mind, I've already commented out, in effect, the existing implementation. It's under a profile. You have to activate that Spring profile for it to work. So the only implementation that we have in the application context is this NIO network file sync. So this should still work. Let's go ahead and run this. Okay, it's up and running. And now we can send another request, and there's our 15713 bytes, just as before. So we've looked at a very simple example using NIO. It worked. It wasn't pretty, but it does work, right? And this is, we've got two classes at least. I haven't done anything smart here. I haven't done any, this is not a very interesting protocol. It's not even an echo server. I'm not even responding with the same payload back. I'm just taking the data in and logging it, basically. But yeah, the code is line 47 all the way down to 104. So I'll call that 60 something lines almost. And that doesn't even include the attachment. So yeah, basically 60 lines for that, compared to the traditional blocking one, which, tons of space. So line 128 to 108. So 20 lines of code. So, 22 lines, right? It's there's a difference there, right? There's a significant difference in readability, ease of understanding, etc. And yet this is the better code. This is the code you want in production, if you can trust it. And that's, I think, part of the problem, is that I don't trust it. So this stuff it's hard, right? It's hard even in the simple cases. It can be downright mind-bending in the hard cases and the corner cases. We're Java a city. NIO is the neighborhood I would never dare venture into after dark, right? So let's talk about something else that makes it a little easier. Netty is a project that was created by Trustin Lee in 2001 or something like that. It's become a de facto standard. It's a tool for building fast, robust, approachable services, and it makes writing correct code easier and more consistent. And if you don't believe me, just take a look at the adapters, right? There's a huge list including Apple, Alibaba, Apache Spark, Basho, Couchbase, eBay, Fitbase, Firebase, Red Hat, Splunk, Sprint, Uber, Squarespace, Spotify, Zynga, VMware, and of course the Spring team and all of our reactive support uses Netty. Netty simplifies writing non-blocking based network services dramatically. It handles things like the state machine that's required for message framing. It handles writing code that can scale and that doesn't block very elegantly. It's amazing, and I cannot wait for you to try it out once. I don't want you to keep using it because, again, you shouldn't be working at that level of abstraction. You should be thinking about it in terms of the higher order business logic in your application. So you should be thinking about it in terms of something like your domain types. And for that, reactive programming is invaluable. It gives you a way to write code in such a way that the smart underlying scheduler of something like Java NIO or Netty can keep the CPU busy while also making it very clean what you're trying to do. You're not dealing with a world in terms of bytes and byte buffers and all that, right? You can just deal with data that comes from something and goes to something. And this, because you've got this single abstraction, also supports those other two goals, ease of composition and robustness. Okay, so we've looked at NIO and we've looked at traditional IO. Let's create another profile here called NIO. And now we've effectively got no implementations. Now we can turn to our next implementation. So this one will use Netty, okay? So we'll say that this is also a service, class Netty network file sync. Class Netty network file sync implements network file sync. Implement that. And we have already some, we know what we got to do. We have to start a service that runs on that particular port of ours. So let's see here. This will be sneaky throws. And we're going to create a event loop group. So NIO event loop group equals new NIO event loop group. All right. Now we're going to create a handler. I'm going to come back to this in a second, but for now, this is a server handler, is it? I think. Whatever. We'll come back to that in a second. Okay. And then let's set up the basic skeleton of the application. So try finally, and we want to do what? We want to create a server bootstrap. And this is the nice thing about Netty, is that you just have to know this one incantation, and it's the same for every network app you write. And it's you can see the obvious opportunities for improving it and so on. So it's just there's like little slots that you can plug in code. I love that about this. The channel that we want to use is the NIO server socket channel. I'm going to send some options. So channel option. There's a lot of good options here that you should definitely spend a few decades memorizing and learning, but for our purposes, we're just going to specify how much data can be kept on the socket in memory before being purged. Okay. Then we're going to specify the handler, and this is just going to be a logging handler. Okay, so logging handler, log level info, and then the child handler. And here's where we can actually initialize things. Channel initializer. And we're going to work with our socket channel implementation. Implement those methods. And voila. Okay. So what we're doing here with Netty is we've got this pipeline. Yeah. And this pipeline you can configure to do whatever you want. Basically, it's a message in, message out. You can have a bunch of they're called handlers, but they're basically filters. They get a chance to act on the request and then act on the response that gets created, and they can each contribute or punt on that process, on that contribution. So here, I want to get the channel pipeline from socket channel dot pipeline, and I want to configure my server handler, right? So that's this business up here, the server handler. Okay, we're going to come back to that in a second. It's null for the moment. Okay, and we're going to kick it off. So future, so channel future equals server bootstrap dot bind to the port, and then we want to sync. Okay, so I'm blocking on that, and then channel future dot channel dot close future dot sync. Okay, and to be honest with you, I don't really understand what this stuff does. I've just kind of always written it that way. I assume it's just waiting for us to be able to bind to a socket. That doesn't need to be non-blocking. We need to bind to a socket. That's fair, right? We can do nothing in the rest of the program means nothing if we aren't bound to a socket. So it's fair that one little thing be blocking. But it's important that we don't keep the system running if there's no reason. And if something, for whatever reason, the system needs to shut down, we want to shut down the event loop group. So we're going to call shutdown gracefully. Okay, let's talk about that handler. That handler is where our business logic lives. And there's a number of different handlers that come out of the box, but we want to create our own here. So we're going to say netty network file sync server handler implements channel inbound handler adapter, and the contract, fairly straightforward. We want to implement the channel read callback. You can see we get just very easy, clean, convenient callbacks that we can use to process the data. We don't have to worry about, writing a loop and should it be concurrent or not or whatever. Just go with what they tell you, right? Okay, so we have a channel handler context and a message. That message could be anything. So what we want to do is we want to read all the data in from the request, and then accumulate it in our byte array output stream. So first things first, I'm going to create a atomic reference to the byte array output stream. Okay, reference, new atomic reference. Good, so that'll be passed in the constructor here. We'll say that. And I'm going to take the data. I'll say if the incoming message is an instance of an abstract buff, then I'll give it I can use smart casting. So now I have a reference to the downcasted type. I don't have to do the downcast anymore myself. And then I'm going to read the data just like I would in Java NIO basically. So I'll say var bytes equals new byte. And here I'm going to do buffer.readable bytes. Readable. Okay. And no, I don't want to say goodbye. I want to say bytes. No, bytes. Okay, good. And with that, I want to read the data. So read bytes. And again, fairly straightforward. And I want to get the reference to the output stream. I want to write. So bytes. Okay, not bad. Good. So if that works, great. The next thing we want to do is when the read is complete, channel read complete, then I want to make sure we actually take the bytes that we've accumulated and write them out. Okay. So here I'll say var BAOS equals this dot reference dot get. If null does not equal BAOS. Okay. We want to get the data from the bytes. So var bytes equals BAOS dot 2 byte array. And if bytes dot length does not equal 0, right, then we want to send them out, don't we? So we can say we want to have the consumer here as well. So we need the consumer, private final consumer of bytes. Goody. Okay, there's that. And we say bytes. No, I say this dot bytes dot accept bytes. Goody. There's our writer. We've written the data out. And of course, we might have more use for this. So this dot reference dot set new byte array output stream. We want to shut down things if we're done with them. Okay, so we'll do the if and all that stuff instead of a try catch. So try catch exception E, and we don't actually care about catch. We want finally. That's what I want. I want to be able to guarantee that certain things get disposed of no matter what. So context dot flush, and I want to close the byte array output stream. Okay, goody. So there's a cleanup. We've reset the reference to the byte array output stream as well. So now the only thing is to actually plug this in. We want this to be an empty byte array output stream. We want to initialize it with a valid reference, right? It'll get reset. The reason we're using an atomic reference is because that's thread safe. So I could just do synchronized or whatever, but it's fine, right? I can do this atomically. I can get a reference and then comparatively set it or whatever. And at the very least, I know that if I'm reading and writing in the same thread, I won't have any issues. Okay, so let's actually go ahead and plug this thing back in to our code upstairs here. So where's my server equals new one of these, right? And again, we can pass in the bytes handler, and we can use this in the implementation right here, okay? So I'm using the channel initializer, I'm using the server bootstrap. This is pretty mundane stuff. This is actually like, unless you have something to say about which options to use and which particular channel type to use and which event loop, and you might, by the way, like I said, there are some pluggable bits here that there's a lot of, there's actually a lot to talk about when we talk about event loop groups, for example. You could use one supporting epoll or U-rings or whatever, and there's some stuff that they do in the Netty project that uses native code that only works on Linux that makes the experience on Linux just second to none. It's just amazing. So once you get it right, that's it. You don't need to worry about it. Really, the business logic, the part where we distinguish this Netty project from every other one that's ever been written, is in the handler adapter, right? This is an inbound handler adapter, but there's outbound ones as well. Okay, so let's go ahead and try it, right? Let's go ahead and run this one. Okay, so it's up and running. Let's go ahead and send some data. And there we are, 15713 bytes. So we have used regular traditional blocking IO, non-blocking IO, and Netty. Now, these days, if I were to build a network service or anything like that, I would start with Netty, or at the very least, non-blocking IO, right? Netty is really, actually, I think, the better choice because it does more than just regular NIO. It's not like it's just a different way of structuring a program so as to take advantage of NIO. It actually has support for stuff that just isn't in the JDK and really should be. All right, my friends, I hope you got something out of this. As always, thanks for watching, and we'll see you next time.